Okay, hey everyone, I have been wanting to make a couple more videos. This was one idea I had today, actually, after helping some folks at work, right? Understand a little bit about how to avoid fighting the borrow checker in Rust, which is, if you're not familiar with Rust, that's obviously one of the big things that uh, a lot of people struggle with, at least not even beginner, right? Because you see intermediate level Rust people that are trying to do something that Rust doesn't quite let you do easily. Because you got to be a little more clever than like a high level language, because it's not going to take, again, it's not going to take care of the memory handling for you, right? And even advanced level people, there's a lot of stuff you can do that you can get yourself in trouble deep down in your how you build your objects that you're handing around inside of your system that you built. So today I'm gonna try to talk about the beginner level, so it's gonna be simple stuff. So hopefully this idea would be like, if you're just trying to get into Rust, which a lot of people are, these are the things you're gonna hit, and then I want to go talk about like how you should probably think about approaching using how you should basically be structuring your code such that you're not going to hit these problems, right? Because if you're coming from something like Java or Python or even Golang, a lot of these issues you're not going to hit because you just don't have to deal with them. They're handled by a system in the background that's a garbage collector slash reference tracker thing, right? For Java, mark sweep, whatever. So you're not going to hit those. And the problem, this all kind of comes from the fact that lots of people are excited about Rust, which is great, but it's not really a high level language like you're used to probably, right? It's still a low level language, but it has high level features, which is great. That's why I like it. You don't have to write crappy old C code and deal with crappy auto tools, right? Like you get cargo, it's there, dependencies, yay, it builds, statically links, it's all great. But like you still have to worry about your memory management, and that's kind of where I think a lot of people trip and fall on their face. So that said, let's just dive right into it. I have a couple examples I want to show over here. Let me move this up a little bit, actually. All right, so I have just a small project here, which I just created. It has my samples in source. So I'm gonna actually, first we'll talk about the borrow checker. So the one thing that a lot of people hit is actually what in C is called a use after free, which is basically a term that is used by the C community for just saying like, you can't, this is something that you're doing that it's not going to work, right? In Rust, you can't really do this because the borrow checker is going to enforce that you can't do this. C, you can do this, but it'll just result in a segfault because you'll be trying to access a pointer that's not there, right? Rust just won't let you create the dangling pointer because at compile time, it's going to make sure that you will never have a dangling pointer because of its ownership principle and borrowing thing. So let's start off by looking at sample one. All right, so sample one, this is a simple example that actually has, we have two coroutines essentially. So we have some object that we built in our function, right? Let me space this out a little bit more. So we build some object. It could be anything. It has to be sort of a complex type. So if this wouldn't quite work with with like a primitive type. So if this was say like an integer or a float, something that is easy to copy. Those are treated a little bit differently by the Rust compiler because it's easy to copy, say, the number 2. If you have the number 2 in some variable in some place in memory and you need to pass it down to another function, it's easy just to make a copy of it, right? And that's actually the correct way to do it because even if you try to pass a pointer to it, the pointer itself is a memory address, which itself is an integer, which again, it's going to pass a copy. So you might as well just pass the copy of the original thing. There's a case there, of course, where if you wanted, you could pass a pointer for the lower level function to mutate it, which we'll talk about what that means later. That gets into the referencing. However, in this case, like this kind of is taken from the example I saw earlier today, which he's creating a complex type. So in this case, we're creating a string. So this is going to be a string that would be created by the from method, right? It's just, oops, it's going to take our literal string here, and it's going to turn it into an uppercase string, uppercase S string, right? And then we'll put that in our variable myString. And then what we have is a function here that we pass it to, which is in this case is a coroutine that we're going to try to pass our string variable to, right? So pretty simple. But you'll notice here in my consuming function, which is named consuming function for a pretty good reason, I'm taking an uppercase string object, just the actual object. I just want, like, I'm saying that the function needs this uppercase type, right? And then we're just going to print it. That's all we're going to do. But you'll notice something interesting here. If I try to compile this, which actually I got to go add it back to my modules so that like, it actually breaks, which will be interesting. Go to lib, comment. Let's comment out the references for now. So if we try to compile this, cargo B, it's going to yell at us. And that's actually the wrong example, so I got to go take that out. One moment. Use to free mod. That's my sample 2 that's failing, also broken. So we try to compile this. It's going to give us some interesting problems here, right? It's going to say this parameter takes ownership of the value. And so when I pass it to my second function as a reference, it's not going to work because it's telling me the value you're trying to borrow a value that actually got moved when we called consuming function, right? Because when we say that myString, it takes a uppercase string, and we pass it directly, like we should, right? Because that's what the function prototype said. So you can imagine this would be like a standard library function that takes an uppercase string, or like maybe some library you're using, right? And it takes an uppercase string. That's just going to consume the myString type. There's really nothing you can do about that. It's gonna need it. Essentially, it's taking, what that means is it's going to take, it needs ownership of the memory that you've allocated here. This isn't typical. There's a couple of functions I know that have taken things that have done like this, although there's a pretty easy workaround to deal with it. This could be something like where you've allocated a buffer and you need to hand it down to like something that is going to like consume the buffer. So like something that might like take it over and write it out to network. There's a couple of ways you could deal with this and be a little bit nicer about it, and it could take, say, like a reference. You could just have the lower level function, the subroutine here, it could take a reference and then clone the string that's given to it. We can also fix this by doing a clone, as it's telling us right down here. Like basically a clone just makes a copy. It's an explicit copy. So remember previously when I talked about how an integer just makes an implicit copy. This one we are going to do the same thing, but we will implicitly tell Rust that you need to create a copy. So we'll actually be using a little bit more memory. So we'll actually have 2 copies of the string in memory, keep one for ourselves, hand one to the function, and then it'll work because we're good for the next function. We will still have ownership of our copy. However, consuming function will have gotten a copy. So let's try that and we'll see how that works, right? All right, so if we do what it said, do a clone, and then we try to compile again, it's all happy because again, we're going to create a copy and it'll pass that to consuming function. So consuming function will get its ownership of a string, but that copy or that string will be a copy of our string, so it'll be independent. Usually that's not really what you want to do. It is useful. Like I said, there's some cases where like maybe the low level function needs to actually be handed a buffer and it needs to have ownership of it. There's a couple reasons for that are probably beyond the scope of this talk. But like I said, that could be a case you run into. Clone's pretty easy to do it. Just be aware you're creating a copy. The other thing you want to do is optimally what you would like to do is pass a reference. And what you'll see, before I do that, talk about that. What you'll see is in referencing function, we're taking a reference to an str, a lowercase s str. So that's actually the built-in string type. We could take a reference to an uppercase string, but that's actually it's less general. So what do I mean by that? That means that we could take that, but it actually, what we can, this function right here is neat because when you say that it takes a reference to a lower str, you can pass in a reference to a big S string, or we could actually pass in a literal as well, and it would take both just fine. Like, it wouldn't complain. We wouldn't have to use any type coercion magic like into or from. It would just take that, and I can actually demonstrate that by just doing string literal value, and we can compile that, and that'll just work because they both basically can coerce to a string reference, a lowercase s string reference str. If you look in the standard library at a lot of their functions, this is what they do. That's because it is the most general. This is one of the first things I learned about Rust, is that if you want to make your string handling methods very general, just take a lowercase str. The other one that that's interesting to take note of here in terms of making your functions general is a lot of things will also take a like if bytes reference fn, so you had like you're passing say a buffer or something, right? And you wanted to make it as most general so people could hand you like a slice or a vec or an array, and it's a bytes type, right? So you don't know if it's text or it could be like encrypted value, or it could be a picture file of just bytes, like that's the bytes of a picture file, right? You don't know. In this case, you could just say like data, and then you can take a reference to an array of U8s. Although this technically is a slice type, a reference to an array is a slice, and that's how you could deal with that, right? And we could, of course, just print that if we wanted to. I think we got to debug print it, so right. So that would work. There's no reason why we would need to do this right here, but that's again one of the more general things that you will see around the standard lib and many other libraries as well. And we'll talk about that more later. So the other way that I could have fixed this, interestingly enough, if I go back to this, so we'll kind of put this back the way it was. Instead of doing a clone here, remember functions run top to bottom, right? So if this ordering of consuming and referencing is not important, what I could do actually is just flip these around, because the consuming function consumes it. Once you consume it, it will move it, and then you won't be at like this reference would be invalid, right? That's the problem. Is essentially you can kind of think of I'm putting something in a variable, and then I'm handing that thing and I'm moving all of that memory to the subroutine, and as the parent routine, I no longer have access to that memory. Well, I might, but I don't know, and the borrow checker doesn't know, and it can't guarantee that, which is why it yells at us, right? And so I can't take a reference to that memory because I literally I can't guarantee I have access to it anymore, right? However, if we flip the ordering around and we just take a reference before we do the move, which, this obviously in some cases that you might not be able to do this because ordering is usually important in your program, right? We can actually compile that and it will work, right? Because we can hand it a reference to our scope variable, and then once we're done with that reference and this function completes and we return up to our parent routine, we can go call the other subroutine and we can do the move because there's nothing else after this function. It just ends, right? Like there's nothing, like we don't need my string anymore. Once the scope exits, Rust is actually going to clean this up, and it's going to deallocate this stack frame for the function of sample 1, right? And so you might as well move it, right? That's fine. So that's my sample 1. That one's kind of obvious, right? Like it's just basically the idea is that if you move something out of your parent scope in consuming functions, you obviously can't reference it anymore because it's technically out of scope now, which is way different than how it works in like Python and stuff. So let's look at sample 2. And I'll have to remember that I gotta put this one back in the compile. So sample 2 is a little bit interesting. This is something that It's actually interesting because this is what happens in something like Python a lot, where say you might or Java, because everything and all the constructors in Java, they return a reference to an object, right? So essentially here, what I do is I'm saying my string, I'm building it, I'm gonna do build something with and return the reference. So this is my function. This is like what a constructor would be, kind of, right? So build a thing and then store it in my string and then print it, right? So this is like how something like a constructor in like Java or Python would work, right? Is, remember, like when you you call the constructor, it hands you back a reference to the object, right? Although the type is technically the object type, right? But in behind the scenes in the thing, it's a pointer to the object, right? Like it's not actually allocated inside of your stack, it's allocated inside of your heap, and then you have a pointer to it on the stack so that anything can find it. You could do that in Rust too. It's a little bit more complicated, but in this case, like what we do is we try to basically build a string, because a string is a complex type, and then we just want to return a reference to it, right? So that's what our function here does, is it returns a reference to a string. This won't work because, well, let me show you first what it says. So, and actually, this one's kind of weird because it's going to complain about my life cycle first. I'm going to get rid of that one just so it doesn't interfere at the moment. So we compile this. It's telling us, hey, you don't have a lifetime on this because I'm handing back a reference. That's not lifetime. This is actually because it can't figure out what the lifetime should be, and it actually, a lot of times when you have a complaining about lifetimes, if you go in and add the lifetime parameters, you're going to find your bug somewhere along the line. It can be a lot of lifetimes. So if I just follow its advice and say, like, yeah, we're going to return a static, which isn't true. That's not how, that's completely, we're lying to the thing right now, right? But we can do that, and we'll see what he complains about after that. And here it's basically going to tell us what the problem is, right? And it actually didn't used to tell you this. This is actually kind of the neat thing about Rust, is like in recent years, it's actually gotten a lot better in the error messages that the compiler throws at you. But yeah, here it's going to say, like, hey, you're trying to return a reference to a temporary value, right? So what it's saying is when we create the string from the string literal in like this function right here, we're trying to return a reference to that, but it's not gonna, that reference is going to be invalidated as soon as that function returns. So what you're returning is you're going to return an invalid pointer. This would actually work in C. This is how a C constructor works entirely. The only difference is that in C, there's really nothing, there's no destructors, right? Nothing is going to guarantee that the memory you just allocated for that string is going to be leaked, right? In fact, that would probably result in a leak unless the function above was somehow like informed that you need to free this, right? Which actually you'll see a lot in C. You'll see structs that have like a build the struct, and then you'll have like a struct name underscore free. So you can call it, you can call free on it when you're done with it, right? In that case, it's actually the developer's responsibility to make sure that the destructor is being called, aka the free method, right? Rust, obviously, you don't have to do that because we have sort of built-in destructors under the drop stuff. And then the compiler will actually figure out when to drop it for you, which is really nice, and I like that. That's one of the reasons why Rust is way better than C, as long as you follow the rules, right? But essentially, this just isn't going to work. So the way you really want to do this is you just want to hand back the actual type. So in this case, we're gonna, the second one is the correct way to do it, right? So if we take that off and just do build thing, and I called this one take because it's taking ownership of the string. So our subroutine here is going to build the string object, and then it's going to return it. This is going to be a move, right? So remember back to the sample one where we had our parent routine actually doing the build and then handing it to a subroutine. This is going to be the reverse of that. Our subroutine is going to build something, and then it's going to return the ownership. This is good in this case because once this function scope is done, the string object will no longer exist. It will be dropped. But here we're actually, before it does the drop, it actually moves the memory from the subroutine stack frame up to the sample2 stack frame, right? And so that'll actually work, although I think it's going to yell at me if I don't comment this out, because that function will just basically never work. There's a couple cases where you can hand back references, but they're a little bit more advanced. I don't know if I'm going to talk about those in this one. Though I've used that case in quite a few things. Now if we try to compile this, it's happy, right? Essentially, this is how you do constructors. This is like constructor 101, right? So you're passing back the actual type, which basically is handing ownership to the thing above. And then you can pass references if you want, just like our sample one, and that's happy, right? That's how you should do it. Which gets me into the next thing that we wanted to talk about, which is when to use references and when to do, which actually we kind of talked about when to use ownership changes, moves, right? Move semantics. And then I'm also going to kind of talk about the different types of references. So there's mutable and non-mutable. So let me go set that up quick. We don't need to have our use after free stuff anymore. All right, so references. All right, so the first one here, I got two examples for this one as well. So the first one's a simple one. This is also pretty much directly from the thing I was helping somebody with today, where you have you have a routine, a function that inside your function you've got some stuff that you need to hand to a subroutine, right? And the question mostly was like, what do I hand it, right? And I don't know why he was confused, because he was using a library and you have to hand the library what it wants. So, right, and most of the time a good library is going to take a reference, because that's what you should be doing. So if there's anything you get out of this, I always try to do a reference, right? Like hand references, because if you hand full things, then you get yourself in trouble. Mutable is not too bad. Mutable is fine too. You just have to make sure that you have mutability over the thing you're handing. This is easy because we own these variables because we have created them inside the sample scope. But like if you say you got this URL back from some other subroutine as a reference, you may not have mutability over it, because it might just be a read-only reference, which would be a major bummer. But you could clone it, right? And then you could have your own copy of it. But it's a copy, remember that, right? So when you do have a reference, you can usually get a full mutable version of it by doing a .clone. There's some caveats to that. Remember to look at the type on if it's clonable or not. Usually the author of that type will implement clone or not. But you are creating a copy, so you have to be aware of that. So it kind of nixes your memory efficiency a little bit, but it's not a big deal. Making copies happens all the time in programs. Just be aware of it. Don't do it in like a triple deep for loop or something. That would probably kill your performance. Yeah, here it's simple. We just have, in fact, these are literals. So like we have an infinite amount of copies of these that we can just reference it anywhere, because they're always going to be inside the binary. Although you don't have to care about that. Long story short, say in here, we're going to make an HTTP request, and they have some subroutine that's going to make the HTTP request for us, right? So we're going to have a string type that's going to be a URL. Obviously, you have to know where you're going to make the HTTP get or HTTP call, and then you have a method. In this case, it's just going to be a simple get. It could be put, post, whatever. It doesn't matter. And then you're going to hand it to the subroutine. So we're going to hand it our URL, and we're going to hand it our method. Then we're going to inspect back. We're going to get a body, and then we're going to print the body, or you could do whatever with it, right? In this case, my subroutine is not actually going to do that. I'm faking it, but just because, like, obviously you could go get the requests library and do this. But here we're just going to show, like, the semantics of what types you would want. If you were going to say, write this subroutine yourself, what do you really want to take in as parameters, and what do you want to return as the type for the person using your API? So you're the library writer, that you're the one providing the subroutine function. What types should you accept from your people who expect to use your library, make the subroutine call, and what types should you be handing back to them, right? Because obviously, if you write your function to take strings, people are going to be pretty annoyed with your stuff because you don't need to own the string. In this case, we're basically taking references to lowercase string because this is sort of it's the most general, and a reference is the least restrictive type, right? Read-only reference in this case, right? An immutable reference, because we're not. Our subroutine doesn't need to mutate the URL. It doesn't need to mutate the method, right? We just need the user to indicate to us what do they want, what action do they want us to take, and where do they want us, what server do they want us to take it on. They're just passing us information. We don't have to mutate these. Nothing really to do with those. We just need to, it's just information they hand to us that we need to do our work. In this case, URL and method. You could obviously add more to here, like URL parameters, headers, right? You can make it as simple or advanced as you want. And then we're going to take those and we're going to use them to make our HTTP request in air quotes, right? In this case, really just reference them. So what you're going to take the URL, you're going to probably parse it, you're going to resolve the host part of the URL, the network location, right? You're going to make a connection out to that server. You're going to format the HTTP request with the rest of the path and the method, right? So you're creating a bunch of stuff internally, but you're just referencing the URL and the method that you created, right? And then eventually they want, obviously, to be a useful library, you need to pass something back. In this case, for HTTP, it would make sense to pass them back the response. In this case, we're just doing the body, and we're going to return the body as a string. Could return it as bytes. You could return it as a complex struct object that has the body internal and maybe some headers. Doesn't really matter. But in this case, we're going to return a uppercase string, because we want to return ownership. Because once this function scope is done, unless we allocate it on the heap, all of the things that we've created will be gone, right? It'll be deallocated. And we obviously want them to be able to still reference the body, right? We don't want the body that we just got back from the network to go away, right? So we'll hand that up to them. So in that case, we're transferring ownership of the body object, which in this case, we've just slapped into a string buffer, right? And so our quick hacky way of doing that is just to basically return a string, and we're just building that from a literal, which is just a small HTML doc I built inline. That's essentially, this is sort of highlights two things of what we just kind of learned about not fighting the borrow checker, which is when you're taking parameters in, just take a reference if you can. There's another caveat to that, which we'll get to in the next example. And if you need to return something that the user expects as some sort of end result, it's generally a good idea just to transfer them all ownership to it, if you can. Sometimes it makes sense to pen them back a reference. Sometimes it might make sense to do like a mutable reference, but those cases are a little bit more complicated, and they're more what you would do on like a struct method, not a bare function like this, because again, there's no state once this function returns, right? If this was a method, then we might have an object somewhere that this method got called on that would still retain state in memory somewhere that we could return a reference to. But that's not the case here. We're actually going to do that in our next example, by the way. In this case, simplest thing to do, return ownership. It's not too hard. This actually, funny enough, this actually is a reference to a heap allocated string object normally. So a string is essentially similar to a vector, which is allocated on the heap, and the vector object that you get back is actually a reference to that memory location on the heap. So it's not like a full making a copy. The move actually doesn't happen. There's still a region in memory of the heap where the body will reside. However, we're just passing back. We're passing back sort of the singleton reference to that memory location. So nobody else can really claim ownership of it. That's the point of why it's kind of a, you can think of it, it's not a singleton in the case, but it's a unique pointer reference, I guess, if you're from the C++ land. Okay, so moving on, this is probably another example where a lot of people are going to build their own structs, sort of struggle with the typing on they should be using. I know it took me a while to figure this out myself, but this is, we'll go over some guidelines on if you're building structs, what kind of types do you want to use for the struct itself, and then also like your methods on it, right? Some of this might be obvious because this seems like an oversimplified case, but every time you build a struct, you kind of have to come back to these things to think about a little bit, right? Because in your type hierarchy that you're building in your system, you know, it's easy to always overcomplicate it, but eventually something's going to come back and bite you in the butt if you're not like really thinking about like the most simple cases that you can, right? So it kind of helps to look at the oversimplified example. In this case, we got our function that we're going to look at is sample2. Sample2 is just going to create a car object, a struct, and then we're going to basically get the make out of that. And then we're going to add some code to this because I want to talk about mutable structs. So looking at sort of our car struct here, we have the struct, obviously, and then we have a make and a model. The make and model types are going to be strings. I chose this because this is an owned type. So that is to say, because it's the actual, like if we put a reference in here, that would be, the car would always be bound to the reference of something else in memory, right? We don't want that. We want the car, we want the car struct to be sort of a self-contained and like encapsulated, right, to use the term from object-oriented stuff, and we want that to be able to be passed around. It has to own its own internals. And so if you wanted to modify them, which we actually don't have any modification here, but we can add that. But in this case, the car, if you the way this actually kind of says is if you own car will actually always own the string, or always own the make type fully. It'll own the buffer, string buffer that holds the make, and it'll own the string buffer of the model, right? So that memory will always be tied together. You don't have any kind of weird shared ownership. If you own car, you own the buffers inside of the car object as well, right? And that's good because if you're trying to pass around references to, trying to pass around ownership of a car and it's got a reference to something else, you're always going to end up with a terrible mess. It's not what you want. So in this case, it's we're not making our two. In this case, we're not making our make and we're not making our model public, right? We're going to try to keep those encapsulated and as read-only attributes. So for the Java people, that's an accessor, or C#, I guess, right? That's the accessor type stuff. We don't have a way to mutate these. We could add a way to mutate these, and actually we will add a mutators for a different thing here. However, when we do that, you'll notice here we're passing, when you access the make method, right, we're passing back again, it's that string reference. The reason we're doing this is because if you have access to car and you're going to try to get the make of the car, there's no real reason to pass back a full string object because you would have to make a copy of it. Because if you were passing back full string here, again, like car owns string, so you would actually you'd have to basically remove the car struct, take the string buffer out of it, and then car would no longer, the car variable would be no longer valid because you can't have joint ownership of a well, you can, but in this case you can't have joint ownership of the string buffer object. Therefore the car type can't just be you can't have the car, you can't own car and have something else own string inside of it. That's a no-no. But we could try that. Russ is going to yell at us. However, if you do own car, you can actually, because this is always going to be in memory inside of this sample2 function scope, you can actually create as many references to the things inside of it as you want, right? And those references will always be valid because they're in the same memory location as car. So if I say, for example, if I actually dropped car here. So this would essentially delete the car object I just created, which is stupid. But if you did this, right, car.make would actually be invalid because we actually can't get a reference to that anymore because I just dropped it. Like, this is the same problem we were talking about before, the borrow checker, right? Like, car value borrowed here after move. It's not really a move because, I guess the drop method kind of quote unquote consumes it, right? But it's gone, right? Like, I don't have that memory value. I just literally created the line before it, which would be, again, it's silly. You wouldn't do this, but the point, making a point, right? So in this case, it's usually okay to return a reference to it. Again, if we say needed to drop car and for some reason we needed to hand somebody the make, like maybe we needed to like hand it to some object that, or some function that puts it into a database, and it needed to have ownership of the make, we could do, you can always do like a to string to get a copy because we're handing back a thing. This should work. So we would have that. So for example, if we did want to like drop ownership, say, before we dropped ownership, we could actually do a let make equals car dot make toString, and this would create a copy, and then we could print it, and this should be happy. And the reason is because essentially what we're doing is we're making this, we get the make as a reference, we turn that reference into a string object, which essentially makes a copy of this internal string. Store that in another function scope, or another function scope variable, yeah. And then we don't really care what happens about car because we just took a copy of the string internally, right? And then we can just use that. So whatever, right? Obviously, this is again, you're making a copy, so you have to remember suboptimality and all that. So let's talk about mutators. By the way, they're essentially the same. I did make model just for the reference, but I don't think there's really much reason to talk about model. Let's talk about mutators though. So let's say we have like a fuel gauge. So we have like gas amount, and we'll call that say that's a U64. I don't know, right? Can't have a negative amount of gas. You could have 0 gas, and then U64 is probably really big. We don't need that much, but hey, U64s aren't that expensive, so fine. And when we build it, we'll obviously have to like say our gas amount. We'll just start it at 0, and then let's make a function we'll call fill, and we'll say do we need to? I don't think we need to return anything here just because it's a mutator, right? Say fill, and then fill has to take, we'll say we'll fill it with some amount of gas, or liters, and then it'll just be a U64 just to make that easy. Right. So some of you will probably see the problem I'm going to have right here. So then we're going to take self, and we're going to say gas amount plus equals liters. That's fine. We don't need to return anything because we're just mutating. And let's actually increase the gas amount. Oh, and then I need to actually figure out how much gas is in it. So pub function. Fuel. Let's just do fuel. I'm returning U64, which is actually really easy because it'll just be a copy type. Right, and here you'll notice here we're gonna return the actual gas amount as a U64 because U64 is a primitive type. We don't need to return a reference because it's copy, copy with a C. So for so U64 is copy. So just return 64 type. Right. So your type can either be copy or it can be clone if you want it to be able to be copied. Marking something as copy means that this will do an implicit copy of it. Marking something as clone means that you have to do an explicit copy of it. If you don't know what that means, just go, you can go read the clone doc, it's pretty good. Most of the time, you'll probably want to make your type clone. Pretty rare that you want to make your type copy. It only really makes sense if you have like small memory type things, and most of those are covered by the basic types, so you really have to worry about it. So we'll do car.fuel, and I want to put that in except instead of make, so it's officer. Yeah, this is the problem that we're going to hit, right? So essentially what we're doing is, because we're trying to mutate an attribute of self, we can't do that because we open it up again. We told the method that we take an immutable reference. So we can't mutate an attribute on self because self is immutable. So in this case, we need to be able to take a mutable reference, right? And that's still a pointer type. It's just, you could think of it as like additional privileges, right? It's a bit stronger of a type. It's more constrictive, less general than just a reference. But if you want to mutate that type, if you want to mutate car, because we're being handed the car object, right? Or that's what self is. You need to say that it needs to be mutable. Normally this doesn't have much of a difference. You just have to add mute. The real problem here is when you get into things like multi-threading. So because you can't, like, many things can have a read-only reference, right? If you have two threads that both have a reference to some read-only thing, that's fine. None of the threads can mutate it. If any thread checks it at any point in time, it'll pretty much always, it's not going to be the same. Like, thread 1 has access to the read-only type, thread 2 has access to the read-only type. Because neither of those threads can actually modify it, they can both read it pretty much indefinitely. And every time they read it, it's going to be like, in that case, it might be the same thing. There might be thread 2 that has a mutable reference, but actually that's not possible because, again, you can't pass a mutable reference between threads. So, meh. Essentially, it's kind of a weird thing, but it does make sense, because if you had like, say you just had a string object that they all had a reference that you read in at like startup time, and then you spawned like a bunch of threads, and they all had a read-only reference to that thread. So like a URL, and then you wanted to go have a bunch of threads crawl that URL path. That would be a valid use case in that case, right? You could spawn off as many threads as you want. They could all reference that one read-only part of the memory, and easy peasy. You don't have to worry about locking because it's all read-only reference, which is actually one of the nice things about that. Mutability, Rust will actually guarantee that this mutable reference is unique, meaning you cannot pass it to another thread. So, because then you would have two threads that have a pointer that would get mutating, which is actually funny because it's actually pretty restrictive, because even in Python, you can pass pointers between threads and happily have each thread mutate the references, right? And it won't complain, which is bad because you're going to totally have a race condition. But it lets you do it. It doesn't. There's no compile check for that. In fact, there's no runtime check either. But in Rust, it's, again, you're getting more guarantees from the compiler, and it's going to yell at you because it's like, hey, you can't pass a mutable reference between two threads. But it's okay in this case because, we only have one function that has the car, access to car. Car is, car. It might yell at us because I didn't make it mutable here. In fact, I think it's going to. Oh, it's not going to because we have ownership, I guess. But in that case, right, it's, oh, because I'm not even calling it. I'm not calling Phil. Dang it. Hang on. Let's say we'll fill it with 10 gallons, right? And then it's going to change. Yeah, now it's going to yell at me. I was like, that's weird. It should have yelled at me. So now we have to say that this car is mutable, which is just I don't know. I think it's kind of weird that you have to do this sometimes, but, I guess it kind of makes sense that you do need to declare it as mutable. Anyway, so now we have a car variable. We're going to mutate it by filling up the car with 10 liters, and then we're going to check how much fuel's in it. I should probably call these just to show you guys that they work, because I'm not doing that. let's say use create, or no, what is this called? Buslit. What's that one called? References. And so references, and that was sample 2, I think. So we'll just call that. Oops. Yeah, that's right. And then it's gonna yell at me because I didn't make that. I didn't make that pub. Yeah. Cool. Well, I'll fix that in a bit. Going back to that, it should work, right? It's just gonna print out fuel. So that's how you mutate. And those are like really the main two types that you want to use, at least as a beginner, is references. So if you don't, like, again, remember, so the order that you generally want to try to do stuff in, and I'm just going to do it at the bottom here, is reference type, or, well, technically it's like ampersand T, right? That's the most general type that you can get away with, right? Like, you can hand that to many threads, you can hand that to many subroutines, it's all happy. If you can get away with passing a ref, pass a ref, right? Returning references is more complicated. Probably when you return, you probably want to consider returning the actual type T. But that's actually, type T is probably the most restrictive type, right? And that is to say, like, passing a T is a big ask, right? Because if you say your function takes the actual type, like uppercase string or uppercase, and what's another example? I keep using string, a vec, right? You're taking an uppercase vec or a path buffer, right? No reference, no mutable ref. You're just taking the actual type. That's actually a big ask by somebody using your API or your function, because they have to give up all ownership over that, right? That's pretty big, right? Like, you can't reference it anymore afterwards. They would have to create a copy, which hurts, memory efficiency. That's a very restrictive type to take. There are cases for it. Usually, like, if you want, like, I've created several APIs I've created in the past where, like, maybe you have a lock and you need to, like, hand that lock object back in. That's when I would take a T, because I want to consume the lock, right? I don't want anybody else to be able to continue to hold that lock object. I'm saying, no, I need, but once you hand me the lock type back, I own it. You don't own it anymore, right? And that's more of a semantic thing, meaning it's more of a, based on the context of that type, which means it being a lock. You don't want people to take a lock and then just keep doing stuff with it, right? And then be able to pass it around the system in various places. Like, that would be bad. Like, that's not what that was designed for. In this case, like, the lock was, you get the thing, do a little bit of work, and then once you're done with that, you have to hand it back into me to commit the changes to the lock thing. And then when they make that call, I consume the lock, so they can't do anything else with it. If they want to continue to make changes, they need to go get a new lock, right? And so that was actually it worked out. That worked out very well in that case, right? But typically, you don't want to take a T and take the actual concrete type unless you're forcing them to transfer ownership of it, right? The next least restrictive is a mute reference T. That's like more if references are more efficient, but in this case you have to mutate the object somehow, which is going to happen. Obviously, systems are going to have to change memory, right? Otherwise, like, what the heck are you doing? I mean, you can always do computing where you're always creating copies, but or using up new memory, right? But to be in a lot of cases, like in I/O, you want to be efficient, so you're going to have to transfer mutable buffers around. And transferring mutable buffers around, you don't want to copy them; you want to pass references. So that's usually where you're going to be dealing with mute Ts. I deal with mute Ts a lot, or mutable references. So if you're doing low-level programming of byte buffers, you'll just get used to that, honestly. Actually, the next one on this is going to be actually T, and I actually forgot about another one, which is actually mute T. Which is like, it's effectively the same. I mean, if you have ownership of the type, you can always create like a mutable type, right? Too. Usually, I guess. There's cases where you might not, but that would be weird. But most of the time, mut t is essentially almost the same as t. Yeah, you have to transfer ownership. You're transferring mutability as well, I suppose. But it's a little bit more restrictive. Like the case is less general. But yeah, again, like it has all the same caveats as T, so you should try to avoid those. There's a lot more advanced types to deal with problems that you'll run into if you can't use these. The one I use a lot is an argt. Argt is essentially a shared reference pointer. So this is actually arcs are similar to how like a Python object works if you're familiar with those, or I suppose it is also similar to a Java object, or a C# one. So if you take, say, like if we went back to our example where we're returning we're trying to build the constructor, we return a reference, right? It's kind of what you can do here, where in Python, when you return an object and you start to hand that object around to various functions in your system, it's actually, every time you hand the object to something, it actually registers that it has a reference to it. So it increments the reference counter. And this is Python, right? Java probably does it slightly differently. At least I'm actually certain it does it differently. But in Python, it's reference counting. So, and that's what this is. It's an atomic reference counter. It's ARC for short. And it wraps a type. So you can essentially take any type. So we could take if we wanted to basically make our car able to be passed around in between multiple threads, you could just wrap it in an ARC. Actually, what you would have to do is wrap it in a mutex, an ARC mutex T, because ARC can guarantee memory safety, but it doesn't get you out of race conditions. To get yourself out of race conditions, then you need a mutex, and the mutex will basically make it so that you can access the inner stuff. And for make and model, you wouldn't have to care because those are readable. However, if you wanted to have multiple threads called fill, then you would have to basically use an arc mutex T to guarantee that only one thread was calling fill at a time, so that you didn't have two things trying to alter the gas amount at the same time, which would cause a problem. Kind of makes sense when you think about it. So in that case, you'd have a mutex T, arc mutex T. So these are like the multi-threading, multi-ownership, I suppose. Those are multiple ownership types. Because essentially what the ARC guarantees is that when the last scope that gets rid of that doesn't use T anymore, it will get cleaned up appropriately. Otherwise, I suppose you could just memory leak it, which should be bad, but that works too. And so that's kind of the end of the stuff that I had for Rust. We went a little bit into multi-ownership, but I hope this helps out some beginners. I think just knowing what structs to use what types to use inside your structs, and what types to pass back and sort of your methods and your subroutines to make a nice API for people. Those are probably the things I appreciated the most as a beginner. So, again, reference type, usually where it's at. You're going to pat on return types, use the ownership type, and then remember about mutability, which usually, honestly, I always forget these things, and then the compiler yells at me, and I just go fix it. It'll happen. Mutability isn't really that one you have to worry about too much. It's usually when you get yourself into like ownership transfer or the multi-ownership between threads type of problem. That's where you gotta be a little bit more careful when things get complicated. Yep, there you go. I'm gonna try to do maybe a couple more of these if there's feedback on this. Maybe get into like the intermediate ones, because there's tons of stuff to talk about on the Rust ownership. It's such a deep topic that you really don't have a lot in other languages because there's no formality to ownership quite like Rust. It's there. Rust is probably the first thing I know that really talks about it and actually turns it into a compile time constraint, I guess I'll call it. But yeah, if you have feedback, add to the comments. like let me know somewhere, and I'll hopefully have more of this ready for people to go. Thanks for watching.